What's new that we need to discuss? Or old for that fact. If anything. Nothing. All right. Shall carry on then. Let's do some more Dijkstra single point shortest path. Just to make sure it's starting to click. All right, let's do some different graphs. No notation for Dijkstra. As I mentioned previously, when we're talking about our graphs, the O notation is no longer in terms of n, rather in terms of the number of vertices and the number of edges, and or the number of edges, I should say. All right, so the number of edges that are in the graph and the number of vertices in the graph are going to affect the complexity of the algorithm. Right, the more possible paths that we can build between a pair of vertices, then the more data we're going to have to process. Right, so the more connected the graph, then the more work that'll be done processing the data. And so just toss in some various edges in here. And non-negative weights. Remember that Dijkstra is a greedy algorithm. So whenever we have greedy algorithms, they all follow the pattern of whenever there's a choice to be made, it's going to take what appears to be the best choice at the time, which is why we do have the requirement of non-negative weights. Still no questions at the moment. Are we wasting our time doing another Dijkstra, or is this an area we want to spend more time on? All right, we will keep on with Dijkstra here then. Let's see. I'll keep that one as a one as well. I think I have all my edges in the graph. All right. Okay, so build our table. So when we have this question on the test, probably give you the table to start off with. The edges we have here. Just vertices 911. All right. All right, so I have one of the columns of vertex we're going to, how we got there, cost to get there, and if we know that's the shortest path that we can have to that vertex. All right, so if you're just given the table as a starting point, test three, no, test three is should be just trees. And make sure get my numbers straight. Yeah, just there's trees. So graphs are a larger topic area than trees. All right, test four. That's in a couple of weeks. Rather 3 weeks. That's the practice test. And that will be on graphs. All right, test three next week. We went over the practice test already, right? Make sure that. Yeah, okay. The final is cumulative, definitely. Can't just forget everything. All right, so whichever entry has no source in the distance of 0, that means that is our source vertex from which we're trying to find the shortest path to all other vertices. All right, so when we're getting to vertex, we need to go ahead and process its edges, right? So we have A to B. So we could get to B from A at a distance of 7. We don't know if that's the shortest path yet or not. A to J for 2, AJ for 2, and AI for 3. All right, so we have 3 choices, and we'll be greedy. Between 2, 3, and 7, we'll take the shortest path. So we will build the path, make that a known shortest path to J. When we decide to do that, so we go ahead and mark it as true. All right, so we processed one vertex. A node has been processed. All right, now from here, we're at J. Some new information. Take a look at see what edges that J has and see if we can improve things, right? So J can go to I for 4 for a total cost of 6. So that's not an improvement over the existing data. So this edge will be processed and discarded. We can get to G from J for a total cost of 3. All right, so the total path with A as a starting point, hop to J for 2, an additional 1 to get to G for a total cost of 3, and then 5 for K. All right. And we can get our greedy steps. So we have, again, 2 3s in the table. And whenever you're doing a min, all right, so we're starting at the first record and working our way down. This path is true, so that value doesn't count. So we have a 7. No data, no data, no data. We have a 3, so 3 is the smallest. 7 was the smallest. 3 is the smallest. Found someone that's not smaller, so it doesn't replace. It's true, so that doesn't count. Not smaller than 3, so it doesn't count. So our first node. All right, so we finished processing J node. In processed. And we'll go start building from G. All right, so we're establishing our shortest path is going to G. All right, so even though we found previously I first, we're using this table. This table is our backing store for the algorithm. True or false is when we've established a shortest path there. All right, again, the logic is since we're building the shortest paths as we're going, right? So we'll just keep building paths and we'll find that this path's out of 4, so this other 3 path will start building later. And we'll get to the point where numbers go beyond 7, so we'll come over here and start building this path to B. We'll just keep on building branches. We end up with a tree when we're done here. And as basically a node gets added to that tree that we're building, it becomes marked as true. Right? The greedy step where we choose to build a path, adding a node into the tree that we're building. All right, so at this point we have, right, so the short stubs here in my graph here, those are potential paths that we could build, unless we've crossed out that edge. So we have potential path to B, potential path to I, potential path to K, and now we need to go ahead and start processing G, right? So we're at G, so we have a couple of edges to process here. All right, G, you get us to K for 1, plus the additional cost to get here, right? As referencing, took us 3 to get to G. So before to get to K, that is an improvement for the existing data. So we will discard the path from J to K. So this edge is no longer relevant. And then we have to F for 7, since there was no path there before. We'll update there. So where are we going? We're going everywhere. We're trying to establish from A as our starting vertex, the shortest path to every other vertex in this graph. Distance is 3, right? Yeah, so the path to get to G is A, J, G, and the cost 2 to get to J, an additional 1 from J. So total cost to get here would be 3, right? Just like it was 2 to get here, which is the same information that's in the table. All right, to get the J, we got there via A, and it costs 2 to get there. To get the G, get there from J, and it costs us 3 to get there. All right, so we have processed all the edges at G, and we can go ahead and be greedy again. Smallest we have is 7, still not smaller. 3 is smaller, 4 is not smaller, so we're going to mark I is the shortest path. All right, so we just finished processing G node. And processed. Choosing I as the shortest path to build next. All right, so we marked I as true, and now we're going to go and process any edges out of it. They haven't already been processed. And that edge is not going to give us any new data. Right, J is in the tree. All right, so let's look at this data at this point. Right, so J is already in the tree that we're building here. Our path is coming with A as the root. The only way this path to have been shorter, now that we've got I and we look at this edge from the other direction, right? It took us more to get to I, right? Initially, the path that was established to get to J would be less than 3, right? Because if it was not less than 3, then we wouldn't have been building those paths. So in order for us to even get to the point where we're going to choose to build this path to I at a cost of 3, all paths that are shorter than 3 or equal to 3 would have already been built. So whatever the cost of this edge is, adding that cost to our cost of 3 here would be greater than whatever path cost we've had already built, which is why we have that clause of weights being non-negative, because if I can make this be like a -4, then that would totally blow the algorithm apart. All of a sudden saying, oh, hey, it only costs -1 to get to J, 3 plus -4, in which case we found a cheaper path here because there's some sort of subsidy or whatever going on to allow a negative cost. So not typical common, or I can't even think of a realistic, well, I suppose if you're looking at travel, right? You look at travel costs, you might have some employers will subsidize commuters. Like if you go on van pool, carpool, whatever, all that fun stuff, but they'll actually reimburse employees for being as a part of a van pool, in which case the costs are actually negative in certain paths, but again, not very common. Okay, so we're now processing the I node, right? So looking at edges coming out of I. Edge in's already been processed. Edge to J has already been processed. We have one new edge to H. Okay, and no one else can get to H. So the data we have here is going to be a replacement of no possible path, or an improvement over no possible path, rather. And that's all the data we can add to our table there, right? So we got 7, 7, 8, and 4. So our 4 path is the shortest path we can build at this point. All right, so we just finished processing the inode. Inode edges have been evaluated and table updated to reflect that. And now we're going to K. That is the shortest path we can build. See a question, why did we keep going from K onward? Because that's not the shortest path. It might be, right, so remember the shortest path is based on the source vertex, not necessarily how far things are from K, right? The shortest distance from K, which when we start looking at minimum spanning trees, we'll see an algorithm that would process things in a similar mindset. It's the shortest path from A, right? And so there might be a shorter route, A, B, C, D, K, to actually get to K by going the long way around here, right? If I had lower costs, if I had like, say we had like a 3 here, yeah, we didn't go to K, where that was. So we don't keep just building the road. So it's not like a depth first search, where depth first search just keeps building on the road that we're on. But we're not trying to build the highway from where we started to as far as we can go. We're building it more of a centralized pattern, more like a breadth first search, where we start here and we basically stay close, where close is a measure of distance on the path as opposed to the hops in the graph. Yes, we're doing the word of the shortest path. So this is going to be similar behavior to like the breadth first search. We're trying to stay as close to where we started as possible, where closeness is measured as the total path cost, which is based on the weights of the edges. And I guess the table. Make that grammar happy. I know. Well, it doesn't like my being word there. Okay, so we're going to K. And we're going to K from G, as the table says here. So we'll go ahead and draw almost straight line to K. K has edges, not yet previously processed. So we'll go ahead and update the table based off that. Path to D, 5 plus the cost to get to K. So let's see, I cost us 3 to get here. K cost us 4 to get here. So 4 plus 5 gives us a 9 to go to D. From K for 9, then we can go to E. From K for 10, and we can go to F. Go to F from K for 11, right? And that is not better than 7. So this edge will be discarded. All right, so our smallest at the moment is 7. 9's not smaller, 10's not smaller, 7's not smaller, 8's not smaller. So our shortest path we're going to start building now here will be to B. Mark that one as true. And so K node processed. B is next to be built. All right, so we marked it as true, which means we have taken our way to B. Cost us 7 to get here. One edge out of B, so we can get to C. So we can get to B. Can really get to C via B for a cost of 15. And the edges are processed. B processed. All right, so who's next? Which path are we going to build next? We don't know KDC yet. We haven't processed these edges. Right now, that's a potential path to C. And we will be replacing that, which is why I had those two edges up there really high and the edges below it small, so that we will replace that quote unquote direct route. Yep. We're building our short paths based on the not the number of hops, but based on the total path length. All right, 2 plus 1 plus 1 gives us that 4 over there. All right, so we'll have a 9 and 11. We'll end up being shorter than 15 at the end. All right, so the way that you would naturally process this, just by you in your mind, looking at the graph, you're just like looking at paths. So you're just building paths in your head, looking for alternate routes. The algorithm is doing something very similar to what you would intuitively do. It's like, well, I can go this way, or I can go that way. Just basically you're looking for detours to see, oh, this road's got a lot of traffic, so I'll hop off the freeway, side street, get around the accident. That's got 3 of the 5 lanes blocked and traffic not moving at all. All right, so based off of this table state, which vertex is going to be built to next? All right, it's not going to be G because G is already in the tree. It has to be one of the falses. I can highlight them. So we have those 4 nodes and H to choose from. All right, so the algorithm, one of you got the right answer. We'll get to the second. All right, so the first path we could build to C for 15. Could build to D for 9. 9 is better than 15, so we'll disregard building to C for now. Could build E for 10. That's not better than 9, so we'll disregard. Could build a 7, or F for 7. 7 is less than 9, so this would be a shorter path to build. Alternatively, we have H, and H is more than 7, so we will build to F. Want to build the shortest path. B is processed. And F is next. All right, so we're going to F because it only costs 7 to get here. The way that we're getting to F is via G. All right, so this is the edge that we build. There are no edges. All right, so F processed. No edges to update the table with. Right, because those edges have already been processed, so that data is already in the table. Yeah, we're always building shorter paths first because that's how we're going to end up with our shortest path, by building short paths. All right, so based on the new table, who are we going to build next? All right, so we have 4 options: H, E, D, and C. All right, because we can't build a path that's already built, so we're only going to be building new roads. Yeah, it's all about the weights. So which weighted path would be the shortest path to build up next? I got one answer. I have 3 answers corroborating, so we're in agreement. H is the shortest path that we can build at this point. All right, so we'll mark that as true. Shortest possible way to get to H will be this path, or 8. All right, H is next, and H has no edges to process, so H is done. As the further we go through this algorithm, more data that we've already completed, right? So we only have 2 edges in the table in the graph at this point that we have not gleaned any information yet from. We have at this point 3 possible paths. We can go to C, as the table shows, for 15. We can go to D, as the table shows, for 9, and we can go to E, as the table shows, for 10. All right, so 9 is shortest path cost at this point. So we'll go to D. Go to D. All right, and we get to D via K. So we'll build out that. To get to D, it costs 9. So we now have 2 edges here. It costs us 11 to get to C via this circuitous route, but that is an improvement. Right? 11 is better than 15. And instead of getting to C via B, we'll get there via D. And then we have the same thing over here. It costs us 2 to get to E. That is an 11 as well. 11 is not better than 10. So this edge will be discarded. All right, and we discarded that edge this round as well. All right, so D is processed. I'll process. E at 10 as C costs 11. Right, all the edges are processed, but all edges are processed at this point, so no other state changes other than marking true at this point. All right, so we just go ahead and mark it as true and mark as true. All right, so we're maintaining two data structures to go through this algorithm. First, the matrix or the adjacency list that represents the graph itself. And second to that, we have our table, which is an array of nodes with these additional data points that we're keeping track of these nodes. We're gonna, for each vertex or node in our graph, we're gonna keep a data point, track how to get there, the cost to get there, and whether or not we know that we've established the shortest cost. Since the table is only going to maintain one inbound edge to the vertex at any point in time, once we're looking at two ways, so let's see. Right, so let's look at I, for example. Right, so we have multiple ways we can get to I. So at a point in time, when we're processing J, we're considering keeping the inbound edge from J as a way to get to I, or keeping the inbound edge from A to get to I. And the edge that we kept is going to be the shortest cost path length. So we had a path of 7. Kind of hard to read. Is this a better color? That's better. All right, so it's 7 versus 3 to choose as the way to get here. And we kept 3 as it's shorter, so we went ahead and discarded that path, that edge that would take us to the I vertex.
So since
And
we already linked J with two smaller weights, we just discard 4.
right, so we're discarding 4 as a way to get to I. Right, so for example, if this edge was 0.5 in cost, then the path 2.5 would have been less than 3, at which point in time we would have then discarded this way to get there. And when I say discard, I mean by what data are we going to hold on to in the table? So how are we getting to I? So the first route that we find to get to I is not necessarily the path that we're going to keep, right? The way I could have done that is if I made this path 8, then the cost path length 6 that we do have here in the table would have been shorter. And then once we got to the point where we're processing J and see what paths we could build from J, we would have discarded the data here in I and would have said, okay, we can get there from J. Instead of it being A3, it would have been J6 because 6 would have been less than 8.
Okay, thank you.
Yep. Questions are always welcome. Just clean up my drawing here so I can grab it. But right, so basically the table represents the scribbles that I have here on the graph. Right, the shortest path from A. I should finish drawing it out. Finish drawing it out. Let's finish drawing it out. Path that way and path that way. And get our screen grab. Right, shortest path to B is from A for 7. Right, so arrow there is 7. Shortest path to C is via D, and this arrow here costs 11 to get there. And to get to D, I get there from K. Right, that path that we built there, and to get to K, we get there from G. Right, so this edge that we built here, and to get to G, get the G from J. Right, our arrow there. And to get to J from A, right? So our arrow here. All right, so this table and this our drawing on top of the graph is the same thing, right? So if we want to show the tree, take graph and blow away the edges that we did not keep. Right, so that went away. This went away. You went away, and there's our tree. Right? A is the root node, has 3 children. J has 1 child, then K has 3 children. G's got 1 child, D's got 1 child, and then I had 1 child. Right, so remember, a tree is a directed acyclic graph, and the paths are going away because it's only A is a single point, shortest path. If we, like I mentioned last week, if we want to do this for all pairs shortest paths, then we would have to run the same algorithm again using every other vertex as a source vertex back on our starting graph. Right. Some algorithms will use this. Let's say starting point. I'm trying to remember spacing on who uses this as a starting point. I'm forgetting now. But yeah. It is Dijkstra's algorithm. Dijkstra has a few algorithms here and there. All right. If I can remember my name correctly here, it should be Floyd Warshall's. See if I can spell their name correctly or not. Wikipedia. All right. All pairs, shortest path. It's just going to be a triply, how do you spell that? Nested loop. Oh, there's one spelled triply. Fewer characters. All right, triply nested loop. That is going to use a jump vertex to compare as an alternate path between a pair of vertices. At the end, we'll know what the cost is, or at least what the shortest cost is, or lowest cost, between any pair of vertices. However, we won't actually know what the path is. Get there. All right, so the code pretty straightforward. So a for loop for all the vertices, a for loop for all the vertices, a for loop for all the vertices. All right, so we're going to compare ij versus ik plus kj. If this value, the sum of these two is smaller than the value in a given cell, We replace that cell's value with that sum. All right, let's see. I have a smaller graph in here already. Well, we'll make this a smaller graph. As you might expect, this is a V cubed algorithm, right? Because it's 3 loops going for the number of vertices, V times V times V, so it's V cubed. So, yeah, 8 vertices, yeah, 8 times 8, 64 times 8, what, 500? Yeah, that's about a lot. Way too much. So we will knock this thing down in size. 5 seems like enough. That's going to be 125 operations as is. All right. This one is going to require us to use the matrix for in-memory representation. Get my dimensions wrong. Let's try that again. Try again. All right, so again, when we're building our matrices or adjacency list, so that all of our representations of any given graph are the same, we have our convention for alphabetical order. All right, so let's see, A, B, C, E, F, so no D, F, E, F. All right, so we need to start with our matrix. So how many on values will there be in the A row? We recall how to build our matrix from a drawing. A is our source vertex. All these entries here would represent its neighbors. What is the degree of A? Terminology, fun terminology. Right, its degree is 3, which is an indication of how many neighbors it has. And that's how many entries we'll have here as not being empty. Right, so A goes to B, A goes to F, and A goes to E. Since it's a weighted graph, right, it won't just be one values, but the costs to get there. And it is a simple graph that has a funny looking for. We will be mirrored again. All right, so we can go B, B goes to C for 2, and F for 7. C is already done. D doesn't exist, so we'll go to E. E is done, and then F is our last one here, so everyone should be already done by that point. And again. All right, so let's double check. We have 1, 2, 3, 4, 5 edges in the graph. Should give us 10 entries. 3, 6, 8, and 10. So that should cover us for what we are doing here. Now, what we'll be doing, so this is our in memory presentation of the graph. Now, what we're going to do, let's see. Oh, Good enough. All right, so what we're going to be doing is going through the loop. Very first time, 1. So the distance of A is greater than the distance of A plus A. We're going to replace the value. All right, so assuming non-negative values, A is not going to be less than A plus A. And the way for them to make that be true would be negative values, right? So -1 is right, not going to be less than the sum. Right, I misspoke earlier. I said less than. So A not going to be greater than A plus A. This is negative value. So if our cost was 2, 2 can't be greater than 2 plus 2. The only way to make that true if we had negative weights. So if negative weights would break this one down as well. So basically the first pass on this, we're comparing itself to itself and not particularly helpful. So we'll go down to the next row. We're comparing, right? So we're still using A as our source vertex here, right? So things aren't changing for a while on the outer boundary here. You can see that K is basically the fixed value in the code here because it's the outermost loop, so it's not changing very much. That's basically representing our source vertex or our jump vertex. Can we get to somewhere shorter than way around? Okay, so the first value we can try to update is B here. What we're trying to basically say is if I go to B and then come back from B, is that, sorry, I said that backwards. I start, if I'm going from B to A, right? So B to A costs 1. Once we're at A can go back to B for 1. And that gives us a cost of 2. So 2 is an improvement over no data at all. So that is going to be an update to the table. Currently B goes to C, but alternatively, we might be able to go to A for 1 and then try to go from A to C. A does not have any connectivity to C, so we're not going to get an improvement on that particular path. So 2 will stay as it is. Right now, B can't get to E, but alternatively, B can go to A for 1, A can go to E for 4, and that's going to be an improvement over no connectivity. Here we have a 7 path. B can go to F directly for cost 7, or alternatively, B can go to A for 1, then from A for 3 more. So we'll go ahead and replace that because we have 4 as a shorter path than 7. So we're going to say that path doesn't work out. We have a better way to get there. Do the same thing for this row. Can't get to AC. Can't get to A. So there's nothing we can do to improve this row. So next up, E here. E is going to see where can we get to. E says using A for 4, we could then jump to B for 1. And that is better than not being able to get there at all. E to A for 4, to C, no connectivity, so no change here. Why can't C go to A? Because there's no edge from A to C. And the path from A to B to C is not yet known. We'll only know that once we've used B as our jump vertex. And then that data will get its way into the matrix. That's a good question. So E, getting to E, via A, 4, and then back. right? A round trip. And then E to F, right? E to A for 4, A to F for 3. 7's better than no path at all. Next up we have F. F can go to A for 3. And then to get to B, 3 plus 1 is an improvement over 7. C, we can't get there from A yet, so no update there. To E, all right, 3 plus 4. All right, what you can see here, we have mirrors, 4 plus 3, now we have 3 plus 4. 1 plus 4, 4 plus 1, 1 plus 3, 3 plus 1. Yeah, I'm just leaving the numbers here so you can see where they're being built from. And then F to A, 3 and 3 back. All right, so I'll get my screen grab. Then I will update 2, 2, 2, 5, 8, 7, 4, 7, 6. And let's grab as well, showing A being used as a jump vertex. And trash all our drawings. All right, so this is what we're doing. We're using as A as our jump vertex on our first path, and then looking at all the other vertices and see if they could hop over there and then hop back somewhere else to see if we can improve things. And this gives us our matrix an updated state. Now we have more data than we had before, where we have roots for some places to get to E and F, but they didn't have roots before, and we have improvements for shorter hops. So next up, all right, so that was going across matrix one time. That was our 2 nested loops going through a path. So I went from 1 to V and J went from 1 to V, and we went across the matrix one time. Now, K increments. Then we're going to use B as our vertex to do our processing. So going to highlight B. And run through the same thing. Right, so using as our jump vertex. See if alternate routes can be chosen. And so go grab the graph again. Let's update our data here. So B to F is now 4. Since we replaced that data, you now have a 7 path. To F, it's not an actual path. And same thing for over here to B. And that should be it. Right, so we found that we can get there for 5. And we can get here for 7. I'm not going to bother with the loops. All right, so we have loops coming back to ourselves on the diagonal. A looping back for 2. It's that information that's going to be useful as the algorithm progresses. But this 7 entry was updated. That was a new data point, and we had a replacement. All right, so we had a 5 and a 4 in the 2 new alternate roots. So that's basically how our graph appears based off of the updated matrix. And we'll use B to see where we can go. All right, so first up, A goes to B for 1. A goes to B for 1. And then we're at B. B can go to A for 1, right? So it's our loop back. All right, so we got a 1 plus 1. A to B for 1, and then B to C for 2. All right, so now we have a way to get to C. 1 plus 5, right? That's not an improvement, over 4. It's right now A. You get to E for 4. And it costs us 80 for 4. Alternatively, A could go to B to try to get to E. Problem is, the way that B gets to E is to first go to A, right? So basically it's go to B, then go back to A, and then go over here. So that's right, not going to be shorter because that dashed line is an indirect route, not improvement. And then we have 1 plus 4, 5 versus 3, not improvement. So we'll leave that alone. Skip reference row. C can go to B for 2. So no data here. We'll go and start the replacement. And C goes to B for 2. And then back again for 2 more. I'm sorry, I'm getting ahead of myself. Now we're going to A. Right, B goes A for 1, so 2 plus 1. Now my 2 plus 2. For C going back and forth. C to B for 2. Now trying to get to E. Couldn't get there before. Since we have a 5, right? So we're using my reference points here, this 2 and this 5, to see if we can improve the data. This 2 and that 4 to improve our data. We couldn't go to C because there was no path information with A as our context. Since B is our reference point, and there's a path known out of B to A to C to F and E based via A, the opportunity to update is going to increase. All right, so that's row C. Now we got E. E can go to B for 5. 5 plus whatever is not less than 4, so don't worry about it. 5 plus 2 is less than nothing. 2. I can draw a 2. The mouse. 5 plus 5 is not better than 8. And 5 plus 4 is not better than 7. And so we're going 4 not better than 3. 4 plus 2. 4 plus 5 is not better than 7. 4 plus 4 is not better than 6. All right, so let me draw the rest of the paths. All right, so we're looking at alternate paths. So we had C to B to F for 6, and C to B for 7, and we have our loopback. So there's a loopback, 2 plus 5, or 2 plus 4, and our 2 plus 1. Okay. All right, so this time B was our jumping off point. And B, all right, say we had decided to start at B arbitrarily instead of going in order in the table, or say we didn't alphabetize the order in the table. Say we had B as the first vertex in the matrix. And so if we were processing B, it would have the same thing. There was no possible way to get to E at that point in time. So it would have found no data update on the record, just like we had first time around when A was trying to be used as a jumping point. All right, so we have updates, which I forgot to draw on my table, so I'll get there in a second. Right, A now has a path to C. Too much data to remember. Get screenshot off to the side. Right, so A now has a path there. Right, that costs 3 to get there. We had C getting to E, and C getting to F. Right, and those go both ways. Get the simple graph. And so we have our 3 there. Our CF, what is CF? 6. And our 7. No. Yeah, 7. Just getting my 3 and my 5 confused there. Let me move this 3. All right. Yeah, it doesn't stop until after every vertex has been updated or processed, right? Triple loop. And it looks like I got my lines slightly off there in my screen grab, unfortunately. All right, we got there 3, 4, 7, 6, 7, and 6. And we had B as our reference. Right, so all of our cells are now filled. That means we'll be able to go ahead and always have a data point of comparison. And we can see what other updates we might be able to get here, right? So now C, these are source vertex. So A goes to C for 3, quite indirectly. And then we're going to see if we can improve any of these values. The only value that's larger is our 4. So we have alternative 3 plus 7 versus 4. No improvement here. B goes to C for 2. 2 plus 7 versus 5. 2 plus 6 versus 4. So no improvement. Skip the C row. E goes to C for 7. No improvements. And F goes to C. So we have no improvements. So we're looking at our options here, right? A goes to C, right? It's not better to get to B. So we decide not to take that path. To E, don't take that path. All right, that's not better. And F. And we chose not to take that path. Coming out of A. B can go to C for 2. And then we have similar things. It's not going to take that path out. Not going to take that path out. Not going to take that path out. E is making similar decisions. E can go to C. And then look at our outbound paths and be like, yeah, nope. And then after the same thing, F went to C. See if we can go ahead and find short routes, but all right, C is way remote. It's a perimeter vertex in our graph here. So it having a likelihood of actually improving distances is not likely, short of the ones that it was already next to. Which means no data changed on that pass. And we can move along to our second to last vertex. Question. We have another node that connected to F with a width of 1. We didn't know its lowest until F. And F. Yeah, F doesn't have any small cost edges here, so we're not going to get much value when we get to F. And E is a perimeter node as well, so not much updating going to go on here as well either. All right, so row by row, using E as a vertex, only values that are larger could we update. Same thing here. Larger than 5, larger than 7, larger than 7. So a whole lot of nothing, no excitement. Processing E. I think F might be the same, as some of you have already noticed. It's not a very connected graph. So our possible routes that we can build out aren't numerous. And I didn't craft this data. All right, so at a potential here, 3 is less than 4, but not when we add in this edge there. 4 is less than 5, but right, the 7's only value. We have a potential here is the loop back and no improvement there. Almost a chance, right? So no state change after processing F. So that final graph, and so this is not that the table actually shows this data, but those are shortest paths, right? A to C, and that's the information that we held on to. The fact that we're getting A to B to C is the actual route to get there. It's unknown in the table. Right, same thing, getting back and forth between B and E, it costs 5. We don't know that A is the way we're choosing to get there, and same thing over here. C to E, cost of 7. We don't know that that's ABC with EABC to get there, right? So if we go back to our original graph state, we're looking at paths. What paths? Right? How can we get to everywhere, right? There's a way to get here, there's a way to get there. Right? Those are ways we get to F. From E, right? A, E, there's a way to get, right? So that's how we get to F, but alternatively, go that way, right? And then vice versa. And that way, if we, assuming we didn't go this way to get to C. And there are a lot of paths that could be built. These are just being the unique ones without any looping, loops on paths. Yeah, that's no fun. All right, and then B, all right, ways that B can get around. And there's only one way to E, there's only one way to C, but to F, we're going to A, or vice versa. Right, and when we did ultimately take right that way, right, we found, well, that deleted a lot more than I planned on deleting. We found that this was the way to go for paths from B, right? There are 1, 2, 3, 4. I suppose I can throw all 4 lines in here. Right, there are 4 other vertices from B's perspective that it might want to go to. Shortest path to C, shortest path to F, shortest path to A, and shortest path to E. Okay, those are what the actual paths are, and then at the end, we are tracking what those costs are. Because of the time complexity on this algorithm, it would be too much to run through the whole thing. Similar thread for Dijkstra, it's too much to run through the whole thing. So what we do would be either a partial update, basically we say use A as a jump vertex, or we'd say using C as the jump vertex with A and B already processed type thing. What is the updated, which cells update more or less? So it'd be a partial run through the algorithms on the test. It's just too time consuming to try to run through the whole thing. And so make sure you read up on the Wikipedia page, all the fun stuff here. All right, cubic, cubic. It's very uncommon to see a cubic algorithm when you're looking at ways to solve problems. I think this is the only one in the class, if I recall correctly, that is actually cubic. Typically, we don't get beyond quadratic, but sometimes we do find that we will run into those situations. All right, let's see. It's like a good time to take a break, so let's go ahead and take 5 minutes, and then we'll continue on. All right, spanning tree. A spanning tree is a tree that spans the entire graph. So we are getting a spanning tree out of Dijkstra when we're running the single point shortest path. Because it's a tree that covers the entire graph. But there's many spanning trees that could exist. So let's say we have a simple C4 graph here. There are 4 possible spanning trees that we could create for this graph. Right? All we have to do is take away one edge from any pair of vertices, and we have a spanning tree. Right? So we have 4 spanning trees here. Now the trick for a minimum spanning tree is we want to choose the one that has the lowest total path length. So if we add some weights here, the objective would be to minimize that cost. So if we build all possible spanning trees and then just sort them or just do a search on the minimum, find the smallest one in that span, in that force more or less that we created, choosing the smallest one of them. All right, so if we look at our total cost here, the total cost for this one is 12. Sum of all the edges in the tree. Here we have 11. So that's a better spanning tree than the first one. Here we have 10. Better yet. And lastly, we have 9. All right, so this is our winning spanning tree. Let's see. Fill color. Right? Because this number is the smallest number of the 4 options, right? 9, 10, 11, and 12 are the weights of the trees, if you want to look at that way, but it's the sum of all the edges in the tree. That's the total cost of that entire tree. That makes this particular spanning tree the minimum spanning tree. So that is our minimum spanning tree. Grab the link. Mini mom. right? So obviously solving all the possible spanning trees for a given graph is going to be way too much work. Way too much work. So we have to take a different approach here. So we'll look at two algorithms. I'm finding a minimum spanning tree. I say a minimum spanning tree because it's possible there are more than one, and we're only concerning ourselves with finding one. All right. Step one, sort the edges. While we don't have a tree spanning the graph, take the smallest edge and add it to the graph. This creates a cycle. Remove the edge we just added. And punctuation. All right. All right, so there's not a whole lot to it. Let's build a graph. Let's see how this goes. Again, remember that our graphing algorithms. And well, let's get a bigger graph. Yeah, a big one in here. Let's go steal it. Remember what I'm copying here. All right. Yeah, we have to do cycle testing. Cycle testing, there are different ways, but basically you do a depth first search for yourself. Will get the job done. All right, so our edges. We have AB7. And we have AI3, AJ2, and BC8, C2. Then we have DE2, DK5, EK6, FG4, K7, G, that's already GJ1, K1, HI5, IJ4, and JK3. All right, so sorted. All right, we just do like a selection sort. Grab our ones. Start grabbing our twos. Grab our twos. Two, two, twos. Twos, all right, grab our threes. All right, run it through a sort. Preferably stable sort. We got any fours in here? There's a four. Five. And see, we got there six. One, six. So I guess two sevens. And I missed somebody. 1, 7, 7, 8. That's always fun. 2 1s, 3 2s. 1, 2, 3. 3 2s, 3 2 3s. 1, 2 3s, a 4. There's my other 4. Skipped FG. All right. Okay, so we will select GJ1 and add to the graph. Let's see here. How much to repeat? All right, so GJ1. That is added to our tree. Someone pointed out FG4. Thank you. Didn't notice the comment. Cycle detect, no cycle. So nothing to do there. If there's a tie, well, then there's a tie. It's entirely possible there's more than one minimum spanning tree. And the actual sort algorithm that we use will drive which of those we'll get. Are we using a stable sort or unstable sort? Right? So when we're building our edges, right? Remember our graph, or when you're building edge lists like we did last week in the lab, we have our source vertex, right? A, B, C, right? A goes to whoever it goes to, and we'll grab the weight. Goes whoever it goes to, grab the weight, and we'll build out our list of edges from here. Once we have that list, we can pass it to a sort. It's a stable sort. It will preserve the order here. So when we had doubles, right, we have these twos. The first one that showed up, the list should stay in front of the second one that showed up in the list. Give us our stability and deterministic, right? So with our convention of how the underlying matrix or list is represented, and assuming we're using a stable sort, then we'll have the exact same processing, which means each time we'll run it will give us a particular of the minimum spanning trees. And the edge that gets added first, that's the tie, is going to win. All right, so we'll go and select GK1 and add. I killed my drawings there. G, J, and GK. All right, no cycle. Next up, go and grab AJ2. Try to add. All right, AJ. No cycle. Let's see. Yeah, we'll get cycles. CD2, try to add. CD. All right, so you'll notice that our tree is discontinuous. And so no cycle. The tree is being built is discontinuous. They are disconnected. So it is a forest at this point in time. But there are no cycles in either of the trees in that forest. So we'll keep on building. All right, and D2. Where is D? There you are. No cycle. Add a I3. That won't create a cycle. Now they're getting connected here, right? So we only have, at this point, F is not in the tree, B is not in the tree, and H is not in the tree. Once all the vertices are in the tree, we are going to stop, just like the algorithm states. We don't have a tree spanning the graph and keep on adding edges. Once we have a tree, we will stop because anything we do after that will be wasted effort. JK3. So the cycle will be detected here. Detected. Trying to add that edge to the graph, right? Creates a cycle here between JK and G. So we have to remove one of the edges from the cycle to break the cycle. Right? Just like we saw with our first spanning trees, we have a cycle, removing one edge, breaks the cycle, we're good to go. So we have a choice between the one edge, or the three edge. Since we sorted at the beginning, we know that the heaviest edge is going to be the edge that we just added. So we're going to remove the heaviest edge, heaviest edge, one we just added. All right, so JK is added, test for cycle, cycle detected, and we will go ahead and break the cycle by removing that edge. All right, add FG4. Where's F and G? All right, so F is not in the graph yet, so that will not create a cycle. It's in the tree, cycle. And IJ4. All right, so I and J are both in the graph. So connecting those two will create a cycle. So we'll remove IJ4. Let's go ahead and draw it out there. Now we attempted to add this edge. What? That created a cycle. So we remove that edge because it's the heaviest in that cycle. And DK5. D and K. All right, so this is joining our trees together. No cycle. Note. Two trees. Now connected. Single tree formed. All right, so we're still looking for B and H to get added in here. All right, we'll have 7, 8 as a possible edges, adding B in, and just 5 that we're waiting for H to get in here. It's the only option since it's in a degree of 1. There's only one possible edge there. All right, at least this 6th edge will be processed before we get there, because it's 7 and 8. And it's just a question of whether or not we process the 7 edge. It just depends on the order of values, and this 8 edge will definitely not get processed because that is going to be heavy. All right, HI5 and high 5. Funny, got a Ready Player One reference there. And no cycle. All right, avoid some scrolling here. Next up after high 5, we'll add EK6 cycle. We will add AB7 no cycle, and we'll have the tree. Let's update my drawing. EK6 create a cycle, and AB7 added form a tree. The BC edge was not considered. To consider it would only guarantee a cycle and guarantee that that edge would be thrown away if we were to even consider that edge. All right. Section lines there. just the white space. All right, so once B is added to the tree, every vertex is in the tree at that point, which means any edges not yet considered are guaranteed to make a cycle and are the ones that will be guaranteed to be removed because of the sorting step. And they're all going to be equal to or heavier than what's already inside the tree. Question, how come EK6 was not discarded since the created cycle? It was discarded. That's why it's a dashed line. Right? It's its cycle. So we dumped it. BC wasn't discarded. It was simply not processed. Right? Once you have a tree, any edges added to the tree are going to guarantee a cycle is going to be created. And if a cycle is created, we would need to remove the heaviest edge in that cycle. That heaviest edge in the cycle is always the most recently added edge because of that sort step, which means we can stop. As soon as we have the tree, we stop processing edges. So I can go into this existing graph, add a whole bunch of edges that were 8 or greater. None of those would get processed because we managed to find a tree before needing to get to them. No, we stop processing. Right, here's our loop condition. Well, we don't have a tree. It's banging the graph. We may need to process every edge to get to that point, or we may only need to process v minus 1 edges to get to that point. Okay, let me do a separate graph to illustrate. We'll go extreme. Go ahead and create a little cycle graph. Excuse me, not cycle graph, a wheel graph. You can click on my shape. Do, 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 do. Wheel gray. All right. Need some weights in here. And we'll make all of these edges in the middle 1. And we'll just make everything on the outside 8. All right, so our minimum spanning tree will be a star graph. In this particular example. All right, so we would have processed one edge would have been added, one edge would have been added, one edge, one edge. I didn't label any of the vertices, so it's possible to know which of those one edges would have been added before the other, but what is guaranteed is these 4 one edges will be added first. If we were to consider adding any of these 8 edges to this tree, that would only just create a cycle. Right? If we wanted to go ahead and draw an edge here, guaranteed to make a cycle, right? Guaranteed to make a cycle, all 4 occurrences, and that would have been the edge that would have been removed, right? So at least v minus 1 edges will be processed. Minus 1 sorted edges. will be processed up to as many as all edges in the graph. Right, and we could force that by having an edge, solitary edge that goes to a vertex and just have that one edge, the heaviest edge in the graph. That one has to be in the tree because it's the only edge that gets us to that particular vertex, which means we had to process them all, but it will vary. All right, prim. I think 1M mentioned here. Yes, 1M. Prim's algorithm. We have a different approach. Step 1, select a node and add it to the tree. As a part of adding a node to a tree, process the edges of that node. And the processing step is see if these new edges offer a shorter distance to nodes that are not already in the tree, and discard their edges. Be greedy. Choose the closest vertex not in the tree and add it to the tree. And then repeat until a tree is formed. All right, so for the above, starting at G. Gotta start somewhere. My name is Glenn, so yeah, I'm selecting G, obviously purely natural. No coincidence at all. All right, G is in the tree. 3 edges. Come out of here. Those are 3 possible vertices. So J, K, and F are edges that we could potentially add to the tree. So we're going to be greedy and choose one of the ones here. So we have J, K. J is first alphabetical order, so we'll add J to the tree. This tells us about more edges. We have these 3 edges coming out. And the edge to A will keep the moment. The edge to I will keep the moment. The edge to K from J we're going to discard. All right, so we're going to be maintaining a table just like we had with Dijkstra's algorithm. We're going to walk through it all, build it first, and then do it again with the table. So we have our tree here, right? J, G tree. And K is a vertex that we could add to the tree. We have 2 options for how we could add K to the tree. We could add it by attaching it the edge to G, or we could add it by attaching it the edge to J. The edge to G has a lower weight than the edge to J. And since our objective is to find a minimum spanning tree, a heavier edge being added to a tree over a smaller edge is not going to get us to the objective. So we're going to just disregard this edge after comparing it to the edge we already knew about. And then we'll carry on. All right, so now we have my little stubs here. We've got a 1, 4, a 2, and a 4. All right, so the smallest of those will be added. We will process the edges. All right, so we have the underlined vertices are those that are now potential to be added. And we're going to grab the smallest one. So we have an option between 2, 4, 4, 6, and 5. So we'll take the smallest one. Smallest distance. A is the closest vertex to our tree that we're growing. A has 2 edges that we haven't already processed. Potentially go to B. B was not already known about, so that nothing to consider there. Now we have an option 2 ways of adding I. Should we keep the edge AI or should we keep the edge IJ? Should we keep the edge that costs 3 or should we keep the edge that costs 4? All right, got 1 vote for AI. Any other votes? It's a 50-50. All right, and why are we taking AI? Why are we discarding IJ? All right, it's smaller, so this edge is not. All right, C and H, we don't know ways to bring them as vertices as to become part of the tree. All right, so we have 7 to B, 3 to I, 5 to D, 6 to E, and 4. Looks like I forgot to X out an edge and even put my nub there, but that one was discarded earlier. All right, so 3 is our smallest. I is now a part of the tree, and we have a 5 edge to consider. All right, 5, 4, 6, 5, and 7. So this edge we found out about a long time ago, finally added to our tree. No other edges to worry about. 7, 5, 5, and 6. All right, so we have choice between D and H. We're going to be using a table. D would have been found first. That's going to tell us about 2 edges. And this 2 is better than this 6. So we'll discard that. Now all entries in our table are filled, but we don't know how to add anywhere else in just yet. 2 2s, C versus Z. C gets added in. Find an 8 edge. We don't care about it. Take the 2 edge we didn't take before. That gets added. No other edges. All right, 5 and a 7. Take the 5. That's added in. And then we take the 7. That's added in. If there is a unique minimum spanning tree, then either algorithm will get us to the same place. All right, now let's go through that stepwise. So we're basically using the same table. So vertex, our source, distance, and known. By way, we write it as in tree. H. Okay. All right, so we'll start at C this time. I have C part of the graph. C is a part of our graph here. 1 second. All right. The distance to C is 0, no source. Yeah, we didn't care about 8 again because we already had our tree. By the time that we would even, let's see, look at my notes. Yes, when C was processed, actually should have been outbound edge there because when we added C, yeah, we should have discarded that 8 because it wouldn't have been less than 7. But we'll see something similar as we process again from somewhere else to start. Right? And where we start is completely arbitrary. Every vertex will be in the tree at the end. So where we start is arbitrary. So C is where we are starting. Real estate work here. All right, so C is in the graph. We are in the tree. 2 edges to process. B8, B8. Whatever. Blank and false are the same thing. CD. All right, so that's the data that the tree knows about at the moment. So we started at C, 2 possible paths to build from. Like before, and be greedy. Those that are not in the tree, choose one to add to the tree, right? And we're intentionally not choosing vertex in the tree because if we were to add an edge to that vertex from one of the other vertices in the tree, that creates a cycle, right? So we don't have to do any cycle detection with Prim's algorithm because it's intentionally choosing someone not in the tree. If you're not in the tree already, it's impossible to create a cycle by adding you to the tree. So we will be greedy and take D into the tree. So we chose D to go into the tree. Now in the tree, and that tells us about 2 edges. Right? We have E. Get to E from D for 2 and K, D for 5. Right? Repeating, choose from 8, 2, and 5. So we'll go ahead and choose the 2. We're going to go ahead and go to E. Build our tree. E is a part of our tree. That tells us about an edge. We have a potential way to get from K, get to K. We already have information about getting to K. It only costs us 5 to get there. This new information at 6 is not an improvement. So, important note difference here, we're not doing a path. We're not building a path. We're not building paths. We are building a tree. So I don't have to do adding. How did I get, what's the cost to get here in the first place? It's not 2 plus 6, like Dijkstra would be doing here. It's just 6 all by itself versus what value is in here. And if the new data is not better than the old data, we will not update the table. All right, so K. Build to K. K is now in the tree and 3 edges of data made available. J for 3. G. Sorry, J from K. So K. K, and 3 sources. So F for 7. G for 1. And I already got the 3 in there for J, right? So there are 3 edges, new information getting to the K node. All right, so we have now 8, 7, 1, and 3 to choose from. Am I going to give you the table or the graph? It could be either way. right? I need to try to ask the questions in such a way that the auto grader can help to the best of its ability. Otherwise, I'm going to have you try to draw a table on canvas. That becomes tricky. All right, so the test mechanism going to constrain us a little bit, but at a minimum, you have to have the graph. And the graph form of the graph could be the adjacency matrix, adjacency list, or just the drawing of it. I try to give it in the easiest form such that the representation of the graph is not getting in the way of the actual algorithm that you're trying to apply to the graph. Okay, so updated the edges. Now we need to make a selection. All right, choose between 8, 7, 1, and 3. So we'll be greedy. We'll pull G in from K. Now part of the tree. Yep. All right. And that gives us 2 edges to consider. Right? And we already had information on J and F in our table here. So let's look at F first, alphabetical order. Not that it matters for how we're processing the edges, but the edges would exist in alphabetical order in the underlying matrix or list. So F could be added to the tree for a cost of 7 from K, or could throw that information away, discard it. Instead of getting to F from K for 7, we will get to F from G for 4. This edge is much cheaper than this edge. And then we'll do the same thing over here. We'll replace the 3 by 1, getting there from G. All right, and who are we taking next? We have 3 options. Which vertex will be added to our tree next? All right, we will take J, and specifically getting there from G. Mark it true. And J's in the tree. 2 new edges of data to process. A 2 and I 4. Really, we don't need this source vertex for this algorithm, but I think it does help show us how we got to where we are. All right, so we've got a 2 and 8, a 4 and a 4. All right, so as you suspect, the 2 will be used. We learn about A3. All right, so that should cause our 8 that we learned about a long time ago to get discarded, as well as that 4 that we just learned about. All right, so B for 7 via A, and I for 3 via A. And 7, 4, 3. I in our tree. Tells us about 5. And move on to the next step. 7, 4, and 5. Take our 4. F in the tree. And that's all that changes. Start any new edges to process. So we have 7 and 5. And that's all that changes. And last vertex, mark that as true, and that's all that changes. And it looks like the same minimum spanning tree, even though we started somewhere else. Now, if there are multiple minimum spanning trees, where we decide to start with prim, that would influence the one that we actually end up with. Right? Say, for example, I had 3 1s here between J, K, and G. Right? Whichever vertex we start at, it's going to tell us about 2 of the 1s, and those 2 will end up in the tree, and the third edge would not, because we found how to get to G or J or K, depending on where we start at, via the other edges first, and unless we find a smaller weight, we're not going to replace our data. All right, there are 2 questions. If we start at G, who would it pick? Well, G, right, these are both 1s, so J and K would be added. J would be added first to the graph. I mean, we started G the first time we started at G. Right? So we learned about J, K, and F. We then had a choice between, well, let me get screenshot first before I start adding to it. All right, we had a choice. If G was the starting point, we had 1, 1, and 4 as our options. Right? The table, J is in the table before K. So the first one would have been selected. Then we would have learned about these edges. That edge would have been thrown away. Then we would have brought K in. We would have then tossed that edge. We would have learned about this edge and learned about that edge. All right. Then second question. Like that also one. We start at J. Yeah, so if we start at J, we'd learn about 2, 4, 3, and 1. And then G would be added first. And that would tell us about another one. And then K would be added. So we'd have had the tree. It's 3 vertice tree here. Try that up again. Okay. Oh, trying to clear drawings over here from this, which is not on the screen. Just don't explode it all away. No, there's one blowing away for me, but right, if we were starting at J, we'd learn about these 4 edges. This one would be chosen. Learn about these edges. This one would be chosen. I don't know how that got extended. It's an interesting automatic completion. All right, so where we start can influence if we don't have a distinct answer. If JK was weighted 1, right, that's the last time earlier. So if we make this weight 1, whoever we start off with, those are the ones we're going to learn about first, and the third edge would be discarded once we learned about it. So if we start off here, these are the 2 ones we find out about, and this edge would be discarded. Right, so that would be different minimum spanning trees depending on whom arbitrarily decide to start off with that first. Well, the table matters insofar as what data is actually populated in the table. Remember, the table starts off sparse in information. It's empty. And the initial state of the table is empty. We don't know anything about the tree. Then we decide to add someone to the tree, and then adding that node to the tree, we will go ahead and inspect the neighbors of that node, what information we have about the edges that take us to those neighbors, and then we'll update the table. Okay, and so from then on, we will learn as we go. So we're feeling our way through. The analogy I like to use for this one, see, we have like, puddles of water forming type thing, right? And there's lots of water drops, big body of water, doesn't matter. But depending on which puddle we're going to start growing first, let's say this is our tree that's growing, or the water as it grows, it's going to naturally attach itself to what's closest to it. Right. So as like say we're dripping water into this puddle type thing, and it's going to, hydrogen bond action is going to grow itself towards whatever's closest to the growing body of water. And this gets added in here, and our body of water grows, and then we span the gap over here, and then this one was just a small addition into our growing puddle. Right, so if we had decided to start dripping water into this puddle here, right, it would have latched on to that one and it kept on growing, whichever distance is closer between these 2 points versus that point. Well, we'll go ahead and assume that's there. Right, keep adding water. Whatever's looks like this one's now closer to our puddle of water type thing, right? The puddle grows, and the puddle grows. Now it's a cactus from the underneath view. In case you're a Minecrafter, which just got some clipping going on there. Okay. Let's see. Let's see. Anything else I want to talk about? Minimum spanning tree. They do have. Where's my? Let's see if I open up. This one's the one that has the GIF. Yeah, there we go. Right, so they started one of these vertices and it just keeps on growing. Wherever's closest grows to it and it just keeps growing the branches there because they're close to where we're growing. And it just the tree grows. Let's see, let's Crescal on this page. There we are. Let's see. All right, Crescal. Some idea, but it's right building its forest approach. Finding those are small, right? Cycles, break the cycles, and it builds them up. Is this one here? Interesting how Wikipedia says this is the first algorithm, and there's no, I guess I just went to the wrong page. The algorithm page instead of the author page. Right? More than one way to fry the egg. I don't remember reading about this particular egg frying, so we're not going to talk about that one. Lots of ways to fry the egg. So, any questions about either of the two ways that we can go about finding a minimum spanning tree? When we start getting to the point where we're talking about traveling salesperson problem, minimum spanning tree is quite useful over there because we can use that as a bounding measure to try to keep our algorithm on track. There are a number of NP problems out in the world. You do. Uh, All right, there's a fun Venn diagram for this. All right, keep my mouse over here so that one's easier to see. If I recall correctly, in the math class, you'll get into it's a little bit more because just into the math behind things here. But some algorithms effectively don't have solutions for problem sets starting at a good given threshold, at least within a reasonable amount of time, because the complexity is just so high in the number of possible solutions, partial solutions getting to where we're going from is incredibly, incredibly high. And so I'll post this again as a link when we get into traveling. I wonder if it mentions it on this page. Yeah, so NP problem here. We're going to talk about this one probably next time. I don't think we'll have time enough tonight. But we're basically trying to create a Hamiltonian circuit such that we get to all of these points. So we're starting somewhere. Say it's right here. And we hit every single one of these points in our sales route and then get back to where we started because we want to come back home at some point. And we want to do it in such a way that we minimize the time spent on the road and the number of paths and the number of cycles that you could create starting where you are and then getting back to where you started quite significant because you're basically using a complete graph as your domain that you're working on. All right, anyways, that's probably it. We'll be talking about that one next week. So for right now, we'll go ahead and take a 5-minute break and then we'll talk about Euler and Hamiltonian. All right. All right, so some definitions here. Let's see if we can find nice page. No, no, no. Path, path, path. All right, I'll have to find some links later, but all right, a path, a graph, a sequence of vertices. If we can create a path, also known as a trail, such that we can use every edge in the graph without repeating, and that path is an Eulerian path. If the starting and ending vertex are the same, then that path is a circuit. And then we have a similar situation. In fact, I'm going to copy paste basically. Bam. If we use every vertex, Hamiltonian. All right, so let's play a game. This is a game you may have played if you were younger. Its objective is to, all right, draw a house. And we want to draw this house without lifting up the pencil. All right, so this is the state we're trying to get to, and we want to go and draw a path to do that. So I could go ahead and start drawing, try to solve this problem here, but that didn't work. All right, so we try again. We'll go ahead and start at the top, see if that works any better. All right, and it didn't work out nearly as well that time. The answer is going to be we need to start at one of the bottom two vertices to solve our house. It doesn't matter which one we want to start at. And the reason, try that again. We need to start at those two vertices has to do with the connectivity of those vertices. All right, so if we look at the degrees of our vertices in our graph, that is this house, we'll see that two of them have an odd degree and the other three have an even degree. when you have a vertex, an even degree, that means for every road in, there's a road out. Right, so it doesn't matter necessarily which road I take because there are a number of solutions to this problem, but there are going to be certain paths that we definitely need to take, right? Because we have our roof up here. Can't work this in such a way. Right, draw with a different color. See if I can change my color here. Guess I need to be in drawing mode before I can change the color. There we go. All right, so try to solve the problem here, but if it is possible. Well, I guess not on this graph. Managed to not break it. Still got the answer there. Let's see. Way to break it. Way to break it. Can I break this? Let's go up first. And over. There we go. Now I managed to break it because I didn't get the roof line. All right, so there is a little bit of a problem with my yellow solution here and the way I consumed my edges. But the key thing is if every edge, excuse me, if the degree of every vertex in my graph is even, then the entire graph is going to be an Eulerian circuit. Conversely, if I have two vertices have odd degrees and the balance even, then there will exist a trail. How to actually solve for that particular trail is a different story, but we're simply going on to whether or not such a thing does exist. All right, so determining if the graph is Eulerian or not. Check the degrees of the vertices. They are all even, and there exists an Eulerian circuit. If they are all even, say for 2, then there exists an Eulerian trail. Uh, let's see. So, yeah, a little while ago, Leonard Euler decided to toss some math at this problem. I forget where this was. Prussia, that's right. I was going to try to say Poland, but I knew that wasn't quite right. All right, so there's a city that has 7 bridges connecting various parts of the city. So basically, you have a vertex. Right, you have a vertex up here, 3 edges coming out. Right, so it's a multi-graph, allowing multiple edges between pairs of vertices. In this case here, and so basically there was I got a gentleman's bet here to try to start somewhere and then traverse every single bridge exactly one time. Right, so the bridges are the edges amongst this graph here. So whether I went ahead and applied some math here and basically look at the degrees, right? With degree 3 here, I need to change my color back to not yellow. That's not quite working. Right, degree 3, degree 3, degree 3, degree 5. All right, so basically came up with a pattern here to show that no, there is not a solution to this problem. And if we went ahead and added another bridge here, change the degree of this to 4 and 6, or excuse me, 4 and 4, then we would at least been able to make a trail. But some of the things in data structures that we talk about, these algorithms have been around for a good long time. Quite a long time. It is one of the advantages of learning data structures. Things don't change very much. All right, so and that if you actually had played this game when you were younger, that game is effectively draw an Euler trail to make this house. And because we have two vertices that have an odd degree, we need to have that to be the starting and ending vertex because we start there. As soon as we leave that vertex, it goes from a 3 to a 2, which means there's going to be a road in and out depending on which road we decide to take. And then we'll have to end at the other 3 because that'll leave it. At one point in time, we'll pass through, consuming 2 of the edges, leaving us with 1 edge. So there'll be 1 road back in. So we cannot make a circuit of this particular graph, right? If we added another vertex at the bottom here and connect those 2, then we could make a circuit. So that a vertex of even degree, and it would make those 2 3s into 4s, and everyone would have an even degree. All right, so certain circumstances may want us to know if we do that, and you'll do similar things in the discrete math class where, in fact, that's one of the things I forgot to talk about for spanning trees. One of the places where spanning trees are useful, like if we're doing infrastructure, say we want to install pipe to deliver water, sewer, whatever it is, to a number of houses, the number of ways that we can lay the pipe to deliver service to this particular sub-development are going to be quite numerous, right? The number of connections you can possibly have if you're just digging tunnels under the ground without any regard for where the roads are, right? That's a complete graph. So the number of possible solutions you can come up with are going to be quite numerous. And the objective is, of course, is to minimize the cost of the installation, right? The objective is to minimally viable product, right? If everyone's getting water, electricity, whatever it is, we're good. And if we can do that with 1 mile of pipe as opposed to 2 miles of pipe, 1 mile is typically preferred, unless there's something special with this other miles, right? So we're trying to minimize the cost, however it is that we're measuring that cost. A minimum spanning tree will be a mechanism that'll be quite useful for that. In fact, I had a student like a decade ago or something like that, worked for it was a civil engineering company or whatever it was, but they basically have engineers eyeball what they thought was the best solution to the problem, and they'd argue over which was the best solution to the problem without taking a formalized approach to what actually is the best solution to the problem. And if this approach is taken using a minimum spanning tree, then we can achieve that. Of course, in the real world scenario, it's gonna be a little bit more complex, especially like for like water, right? You can't just use a 1 inch pipe for the entire length of the subdivision. The pipe that comes into the very first point, 4 inches, 8 inches, however, I have no idea. I'm just making numbers up. Right, you need a larger pipe to deliver how many cubic feet of water. And that is going to be the demand of this area. But the houses that are at the furthest end of the pipe don't require the same thickness of pipe at the beginning. So that's going to require additional complexity to the algorithm, but the same idea would apply. We can try to minimize the trunks and the branching at the beginning so we can keep things down for installing and maintaining. Of course, on the maintaining side of things, that's where a complete graph is less probable because you don't want to start as much as possible have pipe going to other people's properties because getting access to the pipe becomes now more complicated. Not that that's the case. There are plenty of cases where, like gas lines, out here in California, you get that a lot. And before you dig it on your property, make sure you've contacted the gas company and they can tell you if and where gas lines are going underneath the property because digging into a pipe and rupturing said pipe is bad in and of itself, and when you're rupturing a gas line, that's even more so. Okay, Hamiltonian, determining if a graph Hamiltonian is NP, and let me go ahead and grab that link earlier. I guess we actually are going to get to that tonight. Apparently, misjudge things. All right, so NP. And we have the traveling salesmen. So grab those links. All right, so determining I'm getting ahead of myself here. Can be NP. All right, so determining the Hamiltonian circuit on a general graph that is the smallest is problematic. Determining if a graph is Hamiltonian. It all can be done. We'll have to keep an eye out for cut edges and vertices. So let's put that first. Background, get rid of that grid. Supersized checkerboard, all right. Make a graph here. There are cycles that will be attached together. All right, so these two vertices are cut vertices. If we were to remove either of these vertices, from the graph, it becomes two graphs. The graph becomes discontinuous. Either of these causes a problem. Remove them, or if we remove the edge in the middle, all right, so that's a cut edge. We break. All right, the graph becomes disconnected. So there is a Hamiltonian trail in this graph. We just have to be careful where we start. Right, I can't start at this cut edge, cut vertex, because as soon as I try to go around here, I get stuck. And I can't go and repeat this vertex, right? So with Hamiltonian, we're not allowed to repeat vertices. Let's get rid of those drawings. So if instead I start over here, and we can easily go ahead and traverse every single vertex in the graph. So the algorithm, as it is looking to see if there is one or more Hamiltonian paths in this graph or trail, just be careful what vertices it's working on. So basically, I'll start from the perimeter. We'll definitely start from the perimeter and make sure that we're not going through a vertex that causes us to become disconnected from the other ones. All right, solving for the smallest one of all that could be there, that's where things get really, really bad. But, I'll just put the link traveling sales and got my 7 bridges. Now for shaped graphs. Determining if a graph has Euler in. Cycle graphs are always Euler in. Right? They all have degree of 2. Right? All the vertices have degree of 2. Wheel graphs. Chill. Yeah, let's go to star graphs. Star graphs are only Euler in if there are 3 or fewer vertices. Right, we have an S3, we have a central point with a degree of 2, and then 2 vertices with an odd degree. We have an S2, right, one of those ridiculous stars, but each has an odd degree. S1 has a 0 degree. One, anyway, there's no trails, so it doesn't really apply for that one. Wheel graphs. Right, never gonna work. We have a whole bunch of vertices with a degree of 3. Complete graph sometimes, right? K5 has all even degrees, but a K6 has all odd degrees. It's nope. All right, I forgot how to make that small. Good enough. Cycle star wheel complete graph. So cycle graphs always Hamiltonian as well, right? A cycle graph, it's a circuit, right? So easy enough. Star graphs, same story as with Euler. As soon as you go above 3, right? Once you go through that central vertex, you're cutting off paths for star graphs of any size. Wheel graph are always Hamiltonian, right? It's a big old cycle. You start in the middle, start on the outside, work your way around. At some point, you're just going to bounce into the middle. Complete graph. Always, right? You can get to anywhere from anywhere. So it makes it quite easy to hit every single vertex in the graph. Complete bipartite. Leave for you to think on that one. Those are regularly shaped patterns with degrees of vertices are going to be known. So for Euler, you figure it out. For Hamiltonian, that's going to require a little bit more thought. Just do a little experimentation, see what we get. Let's see. All right, okay. All right, so our test, where are we? Where are we? So next week, test 3. Any questions about test 3? And do keep in mind that the height of a tree is -1 if the tree is empty. Try to use the other convention on the test. Probably cost you points. Didn't matter for the program assignment because whatever, that's just change a 0 to a -1 on one line of code. Doesn't matter, but the test is going to be a little bit more particular. If there's only the root, the height of the tree is 0, because the length of the path from root to lowest leaf is 0. Right, if there's no root, then it's -1. If root is null, height of the tree is -1. Okay, that's just the convention we're going with. Remember, there were two conventions. One convention is basically the number of levels or the length of the longest path plus 1, or we have just the length of the longest path. Can I explain number 2 real quick? Number 2, all right, alpha, this is the one that reports things go out of balance. Why would it not be 35? I don't know. Let's rebuild it. So 35, 49, we're still height balanced. 22, we're still height balanced. 27, we're still height balanced. 64, we're still height balanced. 35, did I build this in the right order? 27, 64, 41. Okay, 41. Da, da, da. Right, so at no point in time did anyone complain. All right, so let's change the numbers. Let's see what we get if we build this in the reverse order. So we go from 41, 64, 27, 22. And looks like we're not getting any imbalance there. So let's go ahead and add someone over here somewhere. Doesn't much matter. 41 will become alpha node if we add someone down here. If instead of adding somewhere down there, we add to someone down here, 64 would become the alpha node. Okay, because we got it in balance, either require a single rotation or we require a double rotation. Yeah, 37. We add 37 to this tree. It's going to be happy up to this point. When we get to this point, all right, 3 levels. Oh no, it's still happy at that point. 2 levels. It was quite happy. So it looks like only adding into 49. Apparently I couldn't tell. Yeah, 3 levels. It would have still been happy. So 41 couldn't be alpha. At this point, only 64 could become an alpha at this point. Is there a test 3 prep? Whatever's in the modules, whatever's in the modules. I've moved away from those docs and started creating practice tests. Let's see. So in order to make 27 alpha, we'd have to grow. And so we had 17, 14, still good. So now if we add any of these here, right, then this would become 3 levels, and this one would have just our 1 level. So it causes alpha to go to 20. 27 node in alpha. We'd have to do 1 or 2 rotations to bring this up, which makes this shorter down to 2, and this one bring this up to 2 levels, and then the rest of the tree would get happy as well. The alpha node is the node on the insert path that reports a height imbalance and is the context from which we will do 1 or 2 rotations. Right, the child will be beta, and then if it's a double rotation, we'll have a gamma node. Remember, if we have a right left or a left right, it's going to require 2 rotations. But if it's a left or a right, then just alpha will move up excuse me, beta will move up towards alpha. And balance will be restored. Number 4, if we're talking about a heap, yes. Yep. 4 goes away. 4 goes away, that creates the hole. Last value. Apparently I can't scroll in this mode here. Find my preview button. There we go. All right, 4 goes away, and then 8 is displaced and needs to find a new home because that goes out of bounds of the tree. Remember, our tree or a heap, it's going to build itself, right? Left to right, level by level, and it's going to grow as such, and that's how it maintains its balance. So if we do a delete, right, we create a void at the root, and the rightmost value on the lowest level needs to work its way back down into the tree wherever it goes. And if we keep on deleting, it goes to the root and then works its way back down wherever it goes. And we do that enough time, we get our little heap sort. Next question, difference between height and depth. So height is a tree characteristic, depth is a node characteristic. All right, so a node has a depth in the tree. All nodes at a given depth would constitute a level in that tree. All right, depending on what your numbering is, right? You have the root is at depth 0. And we have all those at depth 1 as its 2 children, right? Then we got depth 2, depth 3, and so on. We don't particularly care about the numbering here. Only numbering that we're holding to is tree height. Right. So we can see if I ask the question, how many levels are in the tree, right? That's a counting problem. So that's 1, 2, 3 counting. Right. I'm not going to ask what's the depth of this node type thing where you'd have to type 2, 1, 2, or 3 type thing. Now that's where it just becomes which convention we decide to go with, and that convention is more arbitrary than the height, right? -1 and non-existence have a pattern in industry, right? If you do like index of something, first valid index is 0, so we can't use 0 as a bad result. So -1, because 0 is a good result or a found result. -1 is a not found result. So a not tree is -1. Right? The height of a not tree is -1. The height of a tree that is barely a tree of its own right is 0. Right, so it's nearly an arbitrary decision, but it's trying to be consistent with other patterns and practices. Depth can be asked, but the number associated with it is not going to be relevant. Right, so if I say, what's the depth of this tree? The answer is a tree does not have depth. Right, if I ask, right, so it'd be terminology, the number that's associated with that terminology wouldn't be matter. So if I ask, like, what's the height of that node? The answer is the node does not have a height. Right, that's a characteristic of a tree. But if I ask you what's the height of a tree, that one actually would be numeric. But the other ways to ask the height question is, how do we determine the height of a tree type thing. And of course, that depends on the type of tree. If it's just a regular tree, that becomes quite difficult. If it's a heap, and we can determine it, right? Because a heap has a particular growth pattern. A heap that has, right, 24 nodes, that has a very specific height, right? Because we have one node, 2 to 3, then we have nodes 4 to 7, then we have nodes 8 through 15, and then we have nodes 16 through 31, right? So I could ask how many levels are in a 24 node heap, right? 1, 2, 3, 4, 5 levels, right? We don't care what level is the root on, right? Is that level 0, level 1? That does not, isn't a meaningful question, right? So if we want to make sure you understand what a level is, right? It's all the nodes at a given depth. All right, so the terminology on that side, so we understand what the term means. This tree would have a height. So 1, 2, 3, 4. Right, so length of the longest path, 1, 2, 3, and 4. So we have 4 hops. So our height would be 4. Right, there are 5 levels. So levels minus 1. You want to look at it perspective of levels or longest path. Right, if we were to put numbers in here, like there's a 7 here and there's a 2 here, let's say or I put a bunch of numbers in here and identify all the nodes, or yeah, that becomes hard because that's the same depth. But yeah, our nodes 7 and 2 at the same level of the tree, right? So if you don't know what a level for a tree is, then you can't answer the question. If you know what the level of the tree is, the answer is no, because they're not at the same depth. Any other questions for the test? Draw the number 6. Number 6. Right, so, right, first level, second level, and I'm going to mess it all up because I'm going to scroll. Or I can make the window bigger. All right, second level, then 4 nodes later, third level. 4. Any more afterwards? Nope. All right, so first level is the root. Its children are 31 and 69. Right, the next 2, right, you always do the math. You have 2i plus 1 and 2i plus 2. What do you want as the right child of 31? 2 times I is 2 plus 2 is index 4, right child. All right, 75. 2 times 2 plus 2, right child. Otherwise, you can put, empty and empty just by going left to right. All right, we'll go ahead and take a 5-minute break and then take a look at program 3, binaries. 3, right? 3 was the trees. Yeah, 3 was the trees. That was due recently, right? When was that due? it was due yesterday. Yes, yesterday. Let's see if you have any problems. Which building the tree again. Take too long. Otherwise, I'll see you next week. If you don't have any questions about the binary search tree code, have a good night. Otherwise, I'll be back in 5 minutes.